galaxies, and here is the trend. The further away you go, the faster you move. And from this, he announced to the world that this means that the universe is expanding. So why did he say that? Well, we can do a little experiment here. So here is a picture of the universe, and through the magic of my computer, I'm going to expand the universe, and now I'm going to overlay before and after. And what do I see? When I overlay before and after, I see that nearby objects have moved a little bit. They have moved a little bit, meaning that if I were to measure their velocity, it would be small. If I look at the distant objects, they moved a lot. I measure their velocity to be high. In an expanding universe, everyone sees that the further away an object is, the faster it moves. And if I can show you it's everyone, I just overlay by a different part of these two images, and I see the same thing. So it fixes our conundrum, and it explains the universe we live in. Now, the reason it explains the universe we live in is not just due to my cartoon. It's because we have a very good theory to work in. And that theory comes from none other than Albert Einstein. In 1907, Einstein had an idea. And that idea was that the acceleration due to gravity pulling on you is exactly equivalent to the acceleration of moving faster. You cannot disentangle the two things. In other words, imagine that you are in a box and you do not know where you're at. You cannot tell if you are on Earth being accelerated by 9.8 meters per second squared, like we are right now, or if you are in a rocket ship that's accelerating at 9.8 meters per second squared. There is no physical way to disentangle those two things. That was his idea. Now, ideas are great, and it took, it turns out, 8.5 years to reconcile that simple idea with a theory of gravity. So it was not easy. And in 1915, he had his answer, and that answer was that space needed to be curved. So it predicted curved space, but it also allowed Einstein to do lots of other things. Now, one of the predictions of curved space is that if you look, for example, at stars behind the sun, they will be in a different position than when the sun's not there, because the sun will curve space with its gravity. And so a person named Sir Arthur Eddington went through and was enamored with Einstein's theory and set out to test it. One would argue he set out to prove it, as I will show you. And here are his pictures of the eclipse. It turned out he went out to one place, Brazil, and his colleague Cromwell went out to by Africa on an island, and those were his images. So the first thing you can notice is Eddington's picture of the eclipse. You can't see any stars. And the reason you couldn't see any stars is it was cloudy. Cromwell, who was actually an astronomer, managed not to get his images in focus. So you can see stars, but they're all donuts because the images are out of focus. So it's rather embarrassing that the theorist managed to get his images in focus, and it was the astronomer, the observer, who managed to get them out of focus. Nonetheless, Eddington was a great theorist. So why was he then the one to analyze this image? Well, he was keen, he did, and in 1919 he announced to the world that these data proved that Einstein's theory predicted how stars moved, and Newton's didn't. We know now that if you analyze this with modern techniques, that the data are not good enough to have made that conclusion. The actual data that showed this was done in 1922. But Eddington gets lots of credit for getting the right answer, even with the data that's not able to do. Eddington made a big splash, and Einstein became famous, literally overnight, for coming up with the theory of general relativity from pure thought alone. That is something that really is quite unique to this discovery, but this is the event that made Einstein famous, not E equals mc squared. So, Einstein did immediately, even before it was shown to be correct, is he used his theories of general relativity to predict something that Newton was never able to do. And that was, how does gravity work with a universe that goes on forever? This drove Newton bonkers, because he couldn't figure out how to make Newton's gravity work in that situation. And so when Einstein worked on this, he got an answer he didn't like. He got the idea that the universe should be in motion. It should be dynamic. It should be expanding or contracting. Hubble hadn't come along until 1929. This is 12 years before. And so Einstein did what any theorist does when they have a great theory that they love, and suddenly it doesn't fit the data. He added a fudge factor. And that fudge factor is called the cosmological constant. And you can think of it now as energy that is part of the fabric of space itself. And his equations of general relativity say that this type of stuff will make gravity push rather than pull. And so by adding this cosmological constant to space, he could balance out the attraction of gravity, and he thought made the universe static. Now it turns out that if a butterfly flaps its wings in one part of the universe, that makes the universe unstable, and it would either start to collapse or expand anyway. So it was a mistake. Of course, 12 years later, he realized when it was shown that the universe was actually expanding, that he could have predicted, amongst everything else, the fact that the universe was expanding. And so he later described it in life as, this was his greatest blunder, or actually the real German quote said, I acted like a donkey. Alright, so Einstein's view of the expanding universe is just a little different than what Schmidt thought when he saw that donkey. The idea of Einstein's universe is that as the universe expands, it's actually space being created. It's not that the objects are moving away from us. It's space is being created and stretched. And so as light travels as a way through space, which is being stretched or created, the light gets stretched and gets redshifted, not because of motion, but because of this expansion of space itself. So it's a little different. So the longer an object's been traveling through space, the more it gets stretched, and you get this redshift, the further the object is away. Now imagine a universe which is expanding. Let's put it in reverse. What happens? Things get closer, 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 and inevitably you get something like a Big Bang. You get a time when everything in the universe is on top of everything else. It's rather hard to imagine how you wouldn't get such a thing if the universe is expanding. It's an inevitable consequence unless you dream up something else. And people have dreamed up other things. But I think it seems to be the obvious thing that we have. So the Big Bang, if we look at this graphically, imagine I have two objects, a galaxy, for example, separated from us right now by some amount. I run the universe back in time. That dotted line runs the universe back in time. And there is some point when the galaxies are on top of each other. That's the time we call the Big Bang. This dotted line is how fast the universe is expanding. The steepness or slope of that line is the current rate of the expansion. We call that the Hubble constant in honor of Edwin Hubble. Now, when I started my PhD in 1989 at Harvard, I decided that the biggest question in the universe that I could think to answer, and that's what we astronomers actually want to do, measure the big question, would be to figure out how old the universe is by measuring how fast the universe is expanding. And so here I am, 3 years, 11 months, and 4 days after I started, showing my PhD supervisor how fast the universe is expanding. And the answer I got, well, that the universe is about 14 billion years old. The only problem is, I knew I'd taken a shortcut. And the shortcut is that that line is straight. But if the universe is full of gravity, the expansion rate of the universe will change over time. Gravity will slow down the expansion of the universe over time. And so that line really should be curved. And And so if the universe is expanding faster in the past and slowing down, the universe won't be as old as 14 billion years old. And that could be a problem, because we know the universe has a lot of stuff in it. We don't quite know how much. And for a perfectly reasonable amount of stuff, it could be that the universe might be only 10 billion years old. And 10 billion years old would be a problem, because that is younger than what we think the oldest stars in the universe are, about 12 billion years old. And we astronomers aren't too fussy, but we do like the universe to be older than the stuff in it. So, a good thing to measure. The other thing is the implications to the future. Imagine a universe that doesn't have much stuff in it. So that's a universe that will be 14 billion years old, will be expanding the same rate in the past as the future. That universe just keeps on getting bigger and bigger because there's very little gravity. It's a universe that expands forever without end. It's a universe that is infinite. On the other hand, if the universe has a lot of gravity, if it has enough gravity, it will eventually slow down and reach a maximum size and go into reverse. And so while both these universe possibilities start with a Big Bang, only the second one ends with the Gnana theory. So that's the Big Bang facts. So, let's do a little bit of review. The slowing down of the universe tells us how old we think the universe will be once we measure the Hubble constant. It tells us the ultimate fate of the universe. And it turns out, because space is curved, it tells us the weight and shape of the universe. So, space, according to Einstein, can be curved. It is curved in 4 dimensions, not 3. We have our 3 normal dimensions plus time. So, if the universe is heavy, and it's heavy enough to eventually stop expanding and go into reverse, then it turns out space is heavy enough so that it bends onto itself in this 4th dimension. It's a universe, if I start here and I head out this direction, I'll eventually come back to where I started. Now, you say, how does that work? Well, the argument I can tell you is that it's sort of like Christopher Columbus going off and saying he was going to come to India alone. So, the problem is that it's bending in 4 dimensions. Now, if you're having problems visualizing how 3 dimensions can bend in a 4th dimension onto itself, you are not alone. I can't visualize it, and I've never met a sane person who can visualize 4 dimensions. So you don't want to be one of the people who can visualize 4 dimensions. Trust me. A light universe naturally bends away from its stuff. It has hyperbolic geometry. One of the experiments I always wanted to do is to have 2 graduate students who I'm going to send off as fast as we can for 1 billion years in rocket ships that go almost the speed of light. And they're going to go in 2 directions. They're going to go out this way and this way. And then after 1 billion years, we're going to stop and we're going to measure the angles between all 3 of us. In the light universe, they add up to less than 180 degrees. In the heavy universe, they add up to more than 180 degrees. Just like triangles add up to more than 180 degrees on the surface of the Earth. Now that may not be obvious to you, but get a piece of string, or 3 pieces of string, look at a globe, and measure a triangle's angles on a globe, and you'll see that they add up to more than 180 degrees. Finally, there's the just right universe. A universe that is precariously balanced between the finite and the infinite. It has just the amount of stuff, such that the universe behaves in a way where triangles have 180 degrees, and everything is sort of normal. Things go on forever, infinitely, but space is not perfect. This type of universe is just right because it's also the prediction of what theorists use to describe the time just after the Big Bang we know as inflation. And so the theorists say if we want to understand the time right after the Big Bang, we need to have this theory, and it predicts the universe should be just like this. So, I love theorists But I really believe in measuring what the universe is doing to keep the theorists honest about whether or not they are right or wrong. So when I came to Australia at the end of 1994, I was presented with an opportunity to do something to add on to my thesis, which is not just measure how old the universe is now through the Hubble constant, but to measure the Hubble constant back in time. And I could do this if I could look far enough away and measure distances and redshifts of objects so far away that their light would take billions of years to reach us. So then I'm looking literally back in time. So imagine an experiment where I can measure the expansion rate back in time. If the universe was expanding at the same rate in the past as the present, then I know the universe is coasting. There's essentially no gravity in it. The universe is light and is going to exist forever. On the other hand, there is a curve, a trajectory for the universe, on which one side, gravity wins and the universe is heavy and finite, and it will eventually end. On the other side of this trajectory, the universe is light, and the universe is infinite, lasts forever. Gravity loses, and the universe expands forever. The reason I could do this at the end of 1994 was due to a couple things that happened. One was an idea. That idea was the ability to use exploding stars, known as Type 1a supernovae, as beacons for measuring distances. So first, let's talk about what a Type 1a supernova is. And to do that, we first need to understand the light of a star. So our sun, in about 4 or 5 billion years, is going to puff up as it runs out of its nuclear fuel, and eventually collapse down to a tiny little star known as a white dwarf star. A star about the size of the Earth, but the mass of the sun. Now, if our sun was born as a binary, that same process happens, except for stars are big and they don't get destroyed by stars as they pop up. And so when the second star is able to pop up, it's able to start putting material on the first star's white dwarf. Chandrasekhar showed that if you reach 1.38 times the mass of the sun, such a star becomes unstable, and in this case, it becomes a giant thermonuclear bomb. A thermonuclear bomb the size of the sun, or even bigger. So these explosions are remarkable because they're so bright. They're 5 billion times brighter than our sun. They take 20 days to reach maximum brightness, and they fade into oblivion. They produce 2/3 of the iron in the universe. Now, all of the steel and iron that we have in here, most of it was made in these types of explosions. So, to use these, well, a group in Chile, who I worked with for my PhD thesis, were out going through the process of discovering these things and measuring how bright they were and how many watts they had. And when they did this work, they found something that was a little unexpected. They weren't all the same brightness. Instead, the ones that were fainter than average rose and fell more quickly than the ones that were bright. And we know now it's because these faint ones produce less iron than the bright ones, which produce more iron. And so these guys were able to calibrate these objects, and they used them in 1994 to measure how fast the universe was expanding. And Mario Gamli from that team was up visiting me and others at Harvard, and he showed me his diagram for the expansion of the universe. And the first thing I noticed is that all of his points lie exactly on the line. That meant his method was providing distances that was incredibly precise. It turned out to be 6% accuracy, which was phenomenally good. Factors of 2 or 3 better than anything else at the time. And so I was very excited about this, and we talked about it. I just finished my thesis, and so we talked about how to do an experiment together. Eventually, this team in Chile was responsible for finding and measuring 29 of these objects, and these provide the fundamental basis of the experiment I'm going to talk to you about in just a second. There was actually another breakthrough in 1994. That was one of technology. In 1994, the technology came about to start discovering very distant supernovae. These type 1a supernovae are very bright, but they're very rare. The last one seen in our own galaxy was in 1604, observed by Galileo and Kepler. So you got to wait around a long time to find them. So what we need to do is look at thousands upon thousands of galaxies. And we need to look upon these in the distant universe where these things are very faint. And so in 1994, two things happened. The first large telescopes, the 10-meter telescopes, were commissioned, the Keck telescopes. These were the first telescopes that had enough size for us to go and measure redshifts of these very bright, distant exploding stars 5 billion years into the past. So before that, we just didn't have big enough telescopes to do it. But the other thing were big digital detectors. In 1994, we got access in astronomy to the first 4 megapixel detectors. So my iPhone has 8 megapixels, but it is 2013. This was 1994, we had 4 megapixel detectors. And so a lot of the technology that we have in imaging today actually grew out through astronomy. These devices were developed for the military, but they were used and developed by astronomers. And so there's a huge amount of heritage in your digital imaging equipment from astronomy. So the problem with these detectors in 1994 is they were huge. This was a time when we had Pentium 100 computers that were orders of magnitude slower than my iPhone. It was a time when we had 1 gigabyte hard drives, but we were going to be taking 50 gigabytes of data per night. And so it was a challenge to go out and figure out how to find these objects. Now, we were not the only team that had this idea to go and look back in time at type 1a supernovae. It was actually 2 teams. One team out of Berkeley, led by Saul Perlmutter, had the idea to go out and look for these things, but they didn't know how to measure distances. The team I worked with, including the people in Chile, had worked on how to measure the distances before discovering it. We talked about working together, but we had very different philosophies on how to do the experiment. And so we ended up with a very competitive race to go through and look back in time. And so Saul Perlmutter led the Supernova Cosmology Project. I led the other project known as the High Redshift Supernova Team. And we had a great competition, but a good competition. A competition that made us work smarter, more intelligent, and quicker than if we hadn't had a competition. We always knew we didn't want to make a mistake, because any mistake we made, the other team was going to point out to the whole world. So, one of the reasons we couldn't work together easily is because they didn't like the way we measured distances, and so we disagreed on it. One of the things we underestimated about them was how hard it was to discover supernovae. So to show you the process, here is an image taken with one of those detectors back in the mid-1990s. This is about 1/1000 of the data we would take at night. There are several thousand galaxies in this image. So we have to find the needle in the haystack. Now I'll show you the needle. It's this little object right here. And the way we find that is by taking not 1 image, but 2 images separated in time. And we wait for the supernova to explode. And my job was to write the software that would find these objects within that morass of data. And so the software had to go through and essentially digitally subtract the images after aligning them and making them look exactly the same. You may well have an app on your iPhone right now that will do that. But we didn't have the apps back in 1994. I had to write them. And so this object, for example, is an object that came from nothing to something between those 2 images. It is an object that is 5 billion light years in distance. It exploded before the Earth was formed. So we can really look back in time. To give you a sense, I take you to Chile in one of our runs, and here we are at the Saratoga 4-meter telescope, and as sun sets, you see silhouetted in black Greg Aldering from the other team. He's the bad. We shared these facilities. These facilities were unique. We both needed the best facilities. And so they would get one night and we'd get the other. We only get 6 nights a year. So as the sky goes by, we have to make sure that everything is perfect. And so here you see Nick Sunset and I, Bob Schomer, making sure the data is perfect. My software is running through the data, trying to find the exploding stars. But it finds a lot of junk. There are asteroids, there are little glitches in the images. And so we have a sweatshop of people sifting through the data that my software is putting out as being potential candidates. Time is of the essence because 36 hours later, on the other side of the planet in Hawaii, we have our few nights of tech time. Those nights are going to allow us to get redshifts of these supernovae, a critical part of the experiment. And there you see Adam Rees, who shared the Nobel Prize with me, taking that data, and who's there, Sol Perlmutter's, of course, on that telescope, because he needs that facility too. So very competitive, but we did see each other all the time, and we even occasionally went out for drinks. We just didn't show him our discoveries. That was always special. So, after 3 very hard years of work, at the end of 1997, Adam Rees was working on the data set, and he sends me an email, says, tell me what you think of this. And the email more or less looks something like this. So let me explain this image. This is an image of which each supernova is a bar. And that bar tells you the uncertainty. So 68.3%, or 2/3 of the time, the correct answer lies in the region of the black bar. So each one measures the expansion rate back in time. And so you can take an average with your eye, and you can see the nearby objects, done by our Chilean part of our group. You can't really see what's going on. But when you look at the distant objects, you can see that not a single one of them lies down in this part of the diagram, where the universe is eventually going to stop expanding and the universe is final. But more interestingly enough to me at the time, is not on average do they lie in the yellow part of the diagram. Indeed, if you do a statistical analysis, you're 99.9% sure that they don't lie in the yellow part of the diagram. So people often ask, what was your reaction when you saw this? Well, it wasn't the idea that the universe was expanding slower in the past than it sped up, that is, the universe is accelerating. That was our eventual conclusion. My initial conclusion was we had done something horribly wrong. So we did not have a eureka moment. Adam Rees, this was his lab book where he sort of did the first calculation. And then from this, we spent several months where each of us went over independently each part of the experiment and compared notes about our answer. When we disagreed, we figured out what we disagreed on. We went through the whole thing that way. It was only after those 3 months that we were able to say, well, I guess that's what our data means. So it was a slow realization that the universe seemed to be speeding up over time. Our work came out in a paper, and it turned out, unbeknownst to us, that the other team, Sol Perlmutter's team, was getting the same crazy answer as us at the same time. And so in 1998, 2 papers were put out stating that the universe was speeding up over time. And it's for this work that we received our Nobel Prize. And so this is the work of not just me, it's an entire team. And I acknowledge that team here, where you see us together in Stockholm a couple years ago. This is the first and only time we had all been together at one point. Because we worked through the internet. We all knew each other, we had all met each other individually, but we had never been together. We were dispersed across 5 continents. And so the internet really is empowering. It allows you to distribute your effort and do things. And of course there we also had Sol Perlmutter's team, shown here, also having a good time. So because I really wish someone would have done this before I won the Nobel Prize, I'm going to show you what it's like when you win your Nobel Prize. So the first thing is when you arrive in Stockholm, they have to get off the plane, and you don't go through customs and immigration the normal way. Rather, they pick you up with a chauffeur on the tarmac, and what I was amused to find was a BMW. I said, not a Volvo, not a Saab, and they said, no, those have been bought out by China, so we're buying Europe. Okay? So my driver's name turned out to be Schmidt. If you know the popular TV show, there's a Schmidt is the name of a driver, a race car driver. So he got us around the streets of Stockholm quickly. You get presented your award by the King of Sweden. And so the Swedes take this very, very seriously. In this case, people in Sweden absolutely wanted to know, what does he ask you? Or what does he tell you? So he says, congratulations on behalf of the Royal Academy of Sweden for the Nobel Prize in Physics. And in my case, he said, thank you very much for the bottle of wine. Because I'm a winemaker, and I had presented him to the Australian government a bottle of wine, which he apparently liked. The other thing that the Swedes give you, which is very novel, is in my case, they gave me a princess. And so this is Princess Victoria, who I got to escort to the ball, which is this amazing ball that they have. So the Swedes, this is the big event in Sweden every year. And we, the scientific community, owe Sweden a tremendous debt for the fact that they put on the world stage science first, and they make a big deal of science. And it really is the event that is for the scientific community to celebrate our successes, rather than the individuals such as myself who receive those awards. So let's get back to our science. What is pushing on the universe? We only have to look back to Einstein's cosmological constant. His great mistake appears to be our great discovery. It turns out that we don't really know it's Einstein's cosmological constant. So we give it a name, we call it dark energy. But his energy of part of space itself can exactly predict or exactly explain our measurements of supernovae. But it turns out we need to have an interesting mix. Our type 1a supernova detailed analysis says you need to have the universe be a mix of 30% stuff where gravity pulls and 70% stuff where gravity pushes. That's what we need to explain our measurement. So you can imagine in 1998 when we announced to the world that, hey guys, you missed 70% of the universe, and by the way, this stuff makes gravity push, not pull. There was some skepticism. I was skeptical. Everyone else was. So what you do in science is you go out and you test this idea. And one of the first tests was done in Australia. It was done through this map of 221,000 galaxies. And you can see that the universe makes sort of a foam. And that foam is caused by the strength of gravity pulling and forming galaxies. Through that foam, you can essentially measure or weigh how much gravity that pulls there is in the universe. And so this measurement, which they made in 2003, showed that the amount of gravity in the universe was about 30% of the way to making the universe just right or flat. That's how we measure things in astronomy. We measure how close, how much stuff there is relative to the enough to make the universe geometrically flat or just right. That dividing line, that critical density that sort of puts the universe into the finite area. Now this is stuff that gravity that makes, this is measuring only pulling gravity, 30%. So the other experiment that came along, I should also say, this also highlighted an age-old problem. That was 5 times more gravity than there were atoms that we could account for in the universe. So we have another problem, not going to talk too much about today, called dark matter. For every atom in the universe, universe, there seems to be 5 to 6 times more gravity than we can account. And so we think there is something called dark matter out there that we need to worry about. The other experiment, we'll just talk a little bit about dark matter. What is dark matter? Well, we don't know, but we suspect it's an undiscovered particle. An undiscovered particle that has properties similar to a neutrino. Neutrinos right now are going through us. They go right through the Earth because they don't interact easily with other matter. Dark matter may be an undiscovered particle that literally interacts with nothing. It interacts a tiny amount probably, but not enough so that it will just go right through the Earth. Things that go right through the Earth are very hard to detect because the way you know things are there is because they interact with things. So it is my hope we may discover this in the next 10 years or so. The Large Hadron Collider may well be able to infer that these things here, but there are other ways we can detect it as well. It has gravity, just like atoms, but it's essentially undetectable. That's what this means. Now the other experiment, got ahead of myself earlier, is from the cosmic microwave background. This is an image taken earlier this year by the Planck satellite of the entire sky of the universe when it was 4,000 degrees, 380,000 years after the Big Bang. This image is showing sound waves splashing around from the time of the Big Bang. You can think that at the time of the Big Bang, the universe was a giant pond, and the Big Bang threw a bunch of gravel into the pond. And what you're seeing is the ripples traveling through the pond. Those ripples travel at the speed of sound. We know exactly the speed of sound because the conditions in the early universe are like what we can create here on Earth. Turns out things travel at 57.7% of the speed of light at this time. So we know how big those splashes are. And we can measure how big they appear on the sky. Now the further away something is, the smaller it appears, except for an expanding universe that's curved, it's a little different. You're going to have to trust me when you take care of those things. But I want to give you an idea about the curvature. If you look at something, it appears differently depending on the space's curve, because space acts like a giant mirror. And so, for example, objects looking in a rearview mirror that's curved appears smaller than one that's curved the other way. The way the curvature of the universe works is objects appear larger in curved, finite space. So we can look at those splashes. You can see how big they appear, and that tells us the curvature of space. Graphically, this is how it works. If the sound waves of the early universe are big, the universe is finite. If they're small, it's open. But these sound waves tell us with very high accuracy that the universe is actually just right, like those theorists predicted from their inflationary ideas of the Big Bang. The universe turns out to be better than 1% flat. We can measure that. It's one of the best measurements we now have of the universe. So let's do some cosmic subtraction. It turns out, I should say, that everything contributes to the universe being flat. Stuff that makes gravity push, or stuff that makes gravity pull. So if we take that, 100%, everything adds up to 100%. 30% of it is attractive, leaving us with 70% mystery matter. Presumably the same mystery matter that we have discovered pushing the universe apart. So where does this leave us? It leaves us with a bit of a mess. Before I go there, I'm going to just, people often ask me the following question. Why do we do astronomy? Why do we do this? And the answer is it's interesting. So the real question is, why do we spend a lot of money to it? And it turns out it's because it's valuable. Things in my area that we're talking about today have developed two of the major revolutions that we have had in the last 30 years. One is by this person, Tim Berners-Lee, who invented the World Wide Web while working at the Large Hadron Collider. That's probably the most valuable thing that has come out of innovation in the last 30 or 40 years. Another thing that came out of Australian astronomy was by this person, John Sullivan, who invented Wi-Fi using the techniques that he was using to go for and look for evaporating black holes predicted by Stephen Hawking. This is Australia's most valuable patent, and it came out this one. So let's talk about the mess then, after that small segue, about the technology that we use to go through and learn new things. New technology in the form of new giant telescopes are what astronomers need to do now. So for example, for me, a telescope like this one, a 39-meter telescope, India is hoping to invest in a 30-meter telescope. Australia is also investing in a 24-meter telescope. I don't know what technologies they will bring, but they are certainly to bring new and interesting. And so technology is what powers astronomy. The reason why I'm here is because I am working with a group here in India on a telescope in Western Australia known as the Murchison Wide Field Array. This telescope is a new type of computer-powered telescope. It is an excuse to develop new high-speed digital electronics, but it's also an excuse to look back to how the first galaxies formed. And so this technology drives our field. This place also is a place where we hope to eventually expand this telescope and the Murchison Wide Field Array into a huge telescope known as the Square Kilometer. All right, back to our story. So if we put everything together, 70% of the universe pushing, 30% pulling, we have a mess. We have a universe which is 5% the atoms that we see in this room, that we measure in our physics labs. 95% of the universe is stuff that we don't know. So you might well say, if you have to make up 95% of the universe, doesn't that mean you just don't understand what you're doing? And that's a perfectly reasonable view, but this model predicts every observation we've been able to make since 1998. And so, like it or not, when we have a model that predicts things, that is the reality that we subscribe to. And this does not just predict little things. It predicts very complicated things. And as long as it does that, it will be the way we describe the universe. And I do not see that ending anytime soon. So, what is the future? Well, the future of the universe is a battle between dark matter, which when we look back in the past of the universe will be smaller, and so a piece of space having dark matter or atoms will be denser. There will be more gravity. And dark energy. Dark energy is different. It's part of space itself. So when I make the universe smaller, there will be less of this stuff relative to atoms. So it's a battle between dark energy and dark matter. The more space expands, dark energy stays the same. The stuff you and I are made out of, this dark matter, becomes weaker. And so we can go through and look what is the battle for the domination of the universe. Dark energy versus dark matter. This is one of the things my colleague Adam Rees has been able to do with the Hubble Space Telescope, looking back not just a little bit, 5 billion years of time, but 10 billion years of time. And he's been able to look back into the past and see that the universe was accelerating, but then in the past, it was slowing down. So gravity and dark matter and atoms dominated the universe here, and then about 5 or 6 billion years ago, dark energy took over. And so the future of the universe is dark energy. Dark energy has won the battle of the universe 6 billion years ago. And so it is going to continue to expand the universe and make us and our atoms less and less important over time. The more space expands, the more dark energy dominates the universe, the harder it can push, the more space it can make, which makes it even more dominant. So the more dominant it becomes, the more dominant it's able to be in the future. Eventually, the creation of space can happen even more quickly than light can travel through it. So, in that first image I showed you of those distant galaxies, the light that is coming from those galaxies right now will never reach us. That light will get stranded in the expansion of space between us and those galaxies. So in the distant future, we're not going to be able to see these galaxies. They will disappear. It's only the fact that there's so many billion years in the past that we can see them at all. So people always ask, well, what's going to happen to us? Well, we're safe, we think. That's because this is the density of dark energy. This is the density of Earth. We're 30 orders of magnitude more dense than the dark energy. And that's because this part of the universe quit expanding 13.5 billion years ago and formed the Milky Way. Attractive gravity has stopped this part of the universe expanding, so dark energy is never able to get its foot in it. Eventually, the nearest galaxies, such as the Andromeda spiral, 3.5 billion years, will merge with us and will form a spectacular new galaxy. I have no idea what we're going to call it. It'll be kind of a boring galaxy because most of the stars will have been formed that can form these galaxies. But if we look down beyond those galaxies, eventually there will be no other galaxies to see because they will be too far away for their light to ever reach us. We will look into an empty universe. But until we understand what's expanding the universe, accelerating the cosmos, anything is possible. We can make dark energy do anything in the future. It is possible that dark energy is something that can change in the future. So our future is not certain. But unless this dark energy changes very quickly and somehow disappears, the universe will, at an ever-increasing rate, expand, fade away, and leave me and my colleagues unemployed. Thank you.